The title of today's lecture is Locks, continued from the previous lecture. Explain why we need to have hardware support for the lock. Let's look at the following code. First, we define the lock structure. It has one flag field here. And then we define two functions, lock and unlock. For lock function, we check if the flag is 0. There's a while statement right here. It gets out of the loop only when the flag field becomes 0. After it gets out of the loop, we set the flag value to 1 and returns. For unlock function, we set the flag to 0. It looks pretty okay, but in actuality, it is not okay. In reality, remember that operating system switches the context among the processes at any given time due to the time interrupt. Let's examine the following scenario. There are two threads, thread 1 and thread 2. And the flag value was 0 at the beginning. The two threads execute the lock function in the following order. Let's consider the line 9 in the previous code. Line 9 is while statement here. So thread 1 checks calls lock and check if the flag is equal to 1. Of course, currently the flag value is 0. So let's consider the following execution scenario. Thread 1 executes line 9, and then context switch happens, and thread 2 executes line 9 again. Then both two threads can enter the critical section right here. So thread 1 calls lock here and then checks whether the flag is 0 or not. It finds the flag is 0. And then at this point, time interrupt has occurred, and operating system switches the control and switches the context from thread 1 to thread 2. Again, thread 2 calls lock and then checks if flag value is 0 or not. It finds that flag value is 0, so it enters the critical section. Before it enters the critical section, it sets the flag value to 1. And then again, time interrupt has occurred again, and then context is switched to thread 1. And then right here, since thread 1 has found that flag value is 0, it also sets the flag value to 1 and enters the critical section. So at this point, thread 1 and thread 2 are both in the critical section. This is violation. So what is the root cause of this to happen? This is because checking the value of a flag here and setting the value of the flag, this is not atomic. So this is the root cause of all the problems because they are performed as separate functions. So it is possible that operating system switches the control to another thread in between, and then the other thread can update the same thing, leading to the race condition. This is a big problem. And there's another issue in spinning length. And there's another issue in spinning. In this lock implementation, the threads wait for the lock to be reset to 0 in the while loop. So if there are more than one CPU, the lock holder can execute in the critical section, and another thread that waits for the lock executes the while loop in the other CPU, which is acceptable. But if there is only one CPU, then the thread which waits for the lock can occupy CPU executing the while statement, while the lock holder is waiting for the CPU in the ready list. So in this approach, a thread that waits for the lock prohibits the lock holder from releasing lock. So these are the two problems of the current implementation. So how can we ensure the atomicity of the operation of checking the flag and setting it to 1? We need an atomic instruction which does both. The first example is test and set operation. Test and set, which is also known as atomic exchange. So this is the C code for test and set, but in actuality, test and set is an assembly instruction. So you can, to help understanding, there are test and set has two parameters. It has address of first one is address, second one is value. So this is address, this is value. So what test and set does is it returns all the value at the memory location, and simultaneously it updates the value of the memory location with the given value. And since this is a single instruction, of course it is executed atomically. This is test and set operation, and it is also called atomic exchange. So this is a simple lock implementation using test and set. Basically it's the same, but so initialization function init is the same as before. But if you look at the lock statement, then there is only a single instruction within the while loop. Test and set lock flag 1 equals 1. It means that sets the value of lock flag to 1 and returns whatever values that was stored in the flag, and do it in atomic fashion. So if the current value of the flag is 0, then it will return 0, and it'll get out of the loop. And at the same time, it sets the value of the flag to 1. If the current value of the flag is 1, then it returns 1 and sets the value of the flag 1. And since it returns the value of 1, it will remain in the while loop. So that's how it works. Let's look at the pros and cons of the spin locks. Correctness, yes, the spin lock only allows a single thread to enter the critical section, but it has a fairness issue. Spin lock doesn't provide any fairness guarantee. So a thread may get unlucky and may get postponed indefinitely. So there is an issue of the fairness in the spin lock. Because as we mentioned before, in a single CPU system, performance of spin lock can be substantial. If there are a number of CPU cores, then spin locks may work reasonably well. The next instruction is compare and swap. Often we use the term CAS as an abbreviation. It tests whether the value at the address is equal to expected or not. If they're the same, then it updates the memory location pointed by PTR with the new value, and it returns the old value at the memory location. This is the C representation of compare and swap instruction. It is supplied 3 parameters. First one is memory location. Second one, third one is memory value. So the second one is value of the flag we expect, and the third one is the value that will be set or stored to the new memory location after the first 2 values are the same. So if the actual value is the value of value that is stored on the memory location, and this is expected value. If those 2 are the same, then we store the new value to this memory location, and it returns the actual value. Using compare and swap, we can implement a lock as follows. So within while statement, we add an instruction compare and swap, and the first parameter is the memory address of the flag. The second one is 0 and 1. So what it means that if the flag is 0, which means that flag is unlocked and lock is available, then it sets the value of the flag to 1. If they are not the same, then the value of the flag will not be changed. Either case, it returns the old value of the memory location. So if the memory location, the flag, if the value of the flag has been 0, then it will get out of the loop immediately. Then what is the difference between compare and swap and test and set? Compare and swap and test and set. Let's say the TAS. And this is compare and swap, and this is test and set. In compare and swap, it performs store operation only when the first parameter and the second parameter are different. Versus in test and set, it performs store operation in every calls to the TAS. So memory traffic that stores the value to memory is going to be much smaller in compare and swap. So this is going to be more memory efficient instruction. In x86 architecture, they implement a similar version of the compare and swap, and we call it a compare and exchange instruction. The next instruction is load linked and store conditional. This is load linked and store conditional. This is plain. I think we are all familiar with the assembly instruction load and store. Load instruction reads the memory variable to the register, and store instruction saves the register value to the memory. That's plain simple. Load linked and store conditional is very similar except one thing. When it loads the variable, it specifies the address memory location. That's simple. And also when you store conditional, it is applied two parameters. Well, the first one is memory location, so it wants to store the value, and the second parameter is the value it wants to store. But there's only critical difference, very, very interesting critical difference. We perform load linked and store conditional, and these addresses are the same. So PTR, and it supplies PTR, and let's say this is 1. Then at this point, it reads the value PTR to some register, $1, and then at this point, it stores the value of 1 to the memory address pointed by PTR. The difference between traditional load link, load and store, and what we are dealing with here, the load link and store conditional, is store conditional value. After it loads the variable, this instruction, if this memory location has been updated by the other thread, then this store conditional fails. Let me repeat. After load link is finished, and when it performs store conditional, if the contents in this memory address has been updated by the other threads, then the store conditional fails. So the store conditional only succeeds if no intermittent store to the address has taken place. If it succeeds, then it returns 1 and updates the value of the pointer by the new value. It fails, and the value at PTR is not updated, and 0 is returned. So this is how the load linked and store conditional is performed. Then let us examine how this can be used to implement a lock. Unlock is the same as before. We set the value of flag to 0. But lock is slightly different. So it is in the while loop and checks whether the flag is 0 or not. If the flag value is 0, then lock, it means the lock is available. If the value of flag is 1, then it means the value of a lock is not available. So using the load link, it checks the value of a flag. If it's 1, then it remains in the loop, keeps checking, waiting for the locks to be available. If the value of the flag is 0, then it gets out of the loop. However, when it gets out of the loop, we have to set the value of the flag to 1 so that no other threads enter the critical section. The problem of separating these two has been solved by test and set and compare and swap via making those two happens as a single instruction. But load linked and store conditional takes a slightly different approach. Here in load linked and store conditional, the process of checking the value of a lock and the process of setting the value of a lock remains apart. But when we set the value of a flag to 1, we check whether it has been updated by the other threads or not. Means that it has been the race condition has happened or not. And if the value of a flag has been updated by the other threads, then store conditional fails, and then it goes back to the original while statement, checking if the lock is available. So that is heart of load linked and store conditional. And this is simplified version of the above lock, making it as a single line. Okay, and there is another instruction, fetch and add. So fetch and add instruction atomically increment the value while returning the old value at a particular address. So this is fetch and add instruction. It is supplied a memory location. So it returns the old value and increases the value of the memory location by 1. And these two instructions are done in a single atomic instruction called fetch and add. So I'm going to explain how this instruction fetch and add can be used to implement a lock. There is a lock called a ticket lock. A ticket lock structure has two fields. First one is tickets and next one is turn. And lock initialization function, it sets the ticket field and turn field as 0. In lock function, the caller calls fetch and add and it obtains a ticket. And then it checks whether the current turn is equal to my turn or not. If they're the same, then it returns and acquires a lock. Otherwise, it spins waiting for my turn. In unlock, it calls fetch and add, and in fetch and add, in unlock function, it increases the value of turn so that the next thread, which has been waiting for the lock, can acquire the ticket. Spin locks are simple and they work, but sometimes it is inefficient because it consumes CPU. Anytime a thread gets caught spinning, it wastes an entire time slice doing nothing but checking a value. So how can we avoid spinning? We need the support from the operating system to avoid spinning, and that we're going to explain the sleep lock. Before we explain the sleep lock, the simplest approach to avoid spinning is just yield. So let's look at this code. There are 3 functions: init, lock, and unlock. As same as before, in lock function, it calls test and set and check if the lock is available or not. When the lock is not available, instead of keeps checking the current status of the lock, in this just yield approach, it calls function yield. So when the lock is not available, it gives up the CPU. That's very important strategy. So when a thread checks whether the lock is available or not and find that lock is not available, then the process relinquishes the CPU and goes back to the ready list and waiting for its turn again. So in just yield approach, when you're going to spin, it gives up the CPU to another thread. So the operating system call moves the caller from running state to the ready state. It is better than just spinning, but every time it finds that lock isn't available, it puts itself on the ready list. So it causes the context switch. And the cost of the context switch can be substantial, and the starvation problem still exists. So we're going to use sleeping lock instead of spinning. In sleeping, we have to introduce another data structure that represents a set of threads that are waiting for a given lock. We're going to use queue. There are two functions. First one is park, and the other is in park. When the lock is not available, operating system puts the thread to sleep. In that area, for that purpose, we call the park. On park is similar to waking up the particular thread designated by the thread ID. So there are two functions you have to remember. First one is park, and the other is unpark. First one, this is the data structure for sleep lock. It has three fields: flag, guard, and queue. The flag field represents the state of the lock, whether it is available or not. And guard is a variable that acts as mutex to protect this construct. The third one is queue. It represents a set of threads that are waiting for this lock. This represents a data structure for sleep lock. Let's look at the actual data structure. There are we're going to deal with three functions. First one is lock initialization, and second one is lock, and the third one is unlock. That is going to be shown in the next page. First, the lock data structure has three fields as before. That says flag, guard, and the queue. And the name of this construct is defined as a lock underbar T. In lock initialization, it has three fields. First one is flag, and the other one is guard. So flag is set to 0, which means the lock is currently available. And guard field is set also as 0, which means that nobody is accessing the lock construct. And also we initialize the queue, which as an empty. When a caller calls lock, it first checks if somebody is accessing the lock data structure. It is achieved by test and set on the guard. So if some other thread is modifying or accessing the lock, then it has to wait. Otherwise, then it gets out of the while loop and accessing the lock data structure. First, we check if the flag is 0 or not. If flag is 0, the lock is available. So then we set the flag value to 1 and unlock the guard. Otherwise, if lock is not available, then we have to add the given thread to queue data structure and unlock the guard, and important function set call park. So in park, we set the thread to sleep. Okay, and the last function is unlock. When we enter the unlock function, we have to check whether the other thread is modifying or accessing this lock data structure. If lock data structure is not available, then we have to wait by checking the test and set function. If the queue is empty, then set the flag to 0. If the queue is not empty, which means that somebody is waiting for the lock, then we have to remove some of the threads from the queue and then set the guard to 0. That's how unlock works. This solution is subject to race condition. Let's consider the following scenario. In case of releasing lock just before call to park, thread B would sleep forever. Let's go back to the few slides back. Here, the thread finds that lock is not available, so it is going to put into park. So it releases the lock, and then just before calls park. Okay, so there are thread A and there are thread B. Thread B. And thread A finds that lock is not available, and then it's going to execute line number 17, and it is going to execute line number 18. But right after executing line number 17 and just before calling write number 18 before it put into the park, okay, the control is transferred to thread B and assume that thread B is holding the lock. And then thread B releases the lock. And then the switch is back to the thread A. And then right after thread B releases the lock, thread A again starts to execute the park. Then who is going to wake up the thread A? This is the race condition. The reason this happens is setting the guard to 0, that it unlocks the mutex and sets to sleep. And this is these are performed in non-atomic fashions. They are executed in split manner. So that is a problem. Then how can you fix the problem? Solaris solves this problem by adding a third system call called setPark. So by calling this routine, a thread can indicate that it is about to park. So it happens to be interrupted and another thread calls onPark. Before park is actually called, then subsequent park returns immediately instead of sleeping. So before releasing the guard, in Solaris, they introduce a new system called setPark. So it gives the system a hint that it is going to put a thread to sleep. Then that'll solve the race condition. Linux provides a futex, which is similar to the Solaris park and onPark. Linux provides two functions. First one is futex wait, and second one is futex wake. In futex wait, it gets two parameters. First one is the address, and the second one is expected. Futex wait puts the calling thread to sleep, and if the value at the address is not equal to the expected, the call returns immediately. The futex wake, it wake one thread that is waiting on the queue. So the address is the queue. This is a sample code. In low-level lock.h in MPT library, they implement a lock using futex. The interesting implementation of this lock is that they use single variable, integer v, to keep track of the lock state as well as the number of threads that are waiting for the lock. That's a very interesting part. And the second thing is that it is highly optimized for the common case where there is not much contention at all and there is one lock holder and he releases the lock and acquires it again. Okay, and there is another type of locks which is called two-phase lock. Spinning sometimes can be very useful because it does not create context switch. So two-phase lock is efficient when the lock is about to be released. So in two-phase lock, lock is at the beginning, it waits for the lock at the spin phase, and then after it fails to acquire the lock after spinning, it becomes a sleep lock. So two-phase lock at the first phase, lock spins for a while, hoping that it can acquire the lock. If the lock is not acquired during the first spin phase, second phase is entered, and in the second phase, the caller is put to sleep, and the caller is woken up when the lock becomes free later. Let me finish this lecture summarizing the contents we have covered. There are largely two themes for the lock: hardware support and software support, OS support. So for hardware support, we cover test and set, compare and swap, and load linked and store conditional. The reason we need hardware support is to test the condition and to set the variable atomically. For those purpose, we have examined three instructions: set, test, and set, compare and swap, and load linked and store conditional. And to avoid spinning, we need a support from the operating system. We examined two instructions, park and park. And also to avoid race condition on wake up and sleep, we covered the contents of setPark. And we also covered the Linux implementation of the operating system lock called Futex and two-phase locks.